Let's look at a few more examples of working with logarithmic expressions using the properties of logarithms. So let's have a look at log base 2 of 4 to the 7th. Now, we could calculate 4 to the 7th. It's not that big a number, but it's not that small a number either. So maybe there's a better way to figure out what this is. And based on our experience with the properties of logarithms, you might wonder, well, what about this exponent? Is there some place else I could put that exponent? And there is a property of logarithms that has an exponent inside the logarithm, and it looks like this. So log base a of some base to a power, so n is playing the role of my power, turns out that it's log base a just of the base, and that exponent n, it comes down in front. I've heard this described as saying that you can roll the exponent off of the log. So if the thing on the very outside of what's inside the logarithm is an exponent, you can move that exponent down in front of the logarithm as a coefficient. You might call this, I guess, the power rule for exponents. An exponent inside is like a product outside. I'm sorry, this is the power rule for logarithms, not exponents. This is related to the power rule for exponents. Remember, the power rule for exponents says a product inside the exponent is like another exponent on the outside. And this is saying sort of the same thing, but in the opposite way. Instead of a product inside and a power outside, it's a power inside and a product outside. Okay. One way or another, we can use this power rule for logarithms to simplify this expression. Our power rule for logarithms says that this exponent on the inside of the log, we can move that down in front as a coefficient. So it's 7 times log base 2 of 4. And log base 2 of 4, that's one we can do in our heads. That's 2. Because 2 squared is 4, and so the exponent we would need to raise 2, the exponent we would need on 2 to get 4 is just 2. And then 7 times 2 is 14. All right. So using the power rule saved us from having to do working with some really large powers of 4. Let's see what else we can do with this power rule for exponents. Let's rewrite this expression, log of the square root of u times v squared, but without using any exponents. First of all, just a quick note that remember when there isn't a base on log, it's actually base 10. That's called the common log. So this is log base 10 of the square root of u times v squared. And there's a square inside of the square root here. So we would like to somehow get that square somewhere else. And you might think, hey, let's use the power rule for logarithms, and that's a good idea, but remember the exponent, to use the power rule for logarithms, the exponent has to be the very last thing that happens before the logarithm. In this situation, the log can't really see that square because the square root is in the way. So we somehow need to deal with the square root and also the product that's right here. So how could we deal with the square root in a product? Well, a square root actually is an exponent. So we could rewrite this as log, and again, that's common log, of u times v squared to the 1/2. So now there are a couple ways to handle this. We could take this power of 1/2, since it's on the very outside of the stuff inside the logarithm, we can move it down in front as a coefficient. That's what the power rule says. So we get 1/2 times common log of u times v squared. And now it's tempting to say, hey, let's take this square to move it down in front. But we can't do that because the logarithm can't really see the squared yet. The logarithm sees the last operation that happens inside of these parentheses. And the last operation inside of these parentheses is actually this product. So we can use some property of logarithms to deal with the product, but we can't yet use a property of logarithms to mess with this squared here. But thinking about the product, fortunately there is a property of logarithms for a product, and that's the product to sum property for logarithms. So we get 1/2 times, And now we can break this product up inside into a sum outside. So log of u plus log of v squared. Now finally, this last logarithm does see that squaring, because that squaring is the last operation that happens before the log happens. So now finally we can use the power rule to get rid of that squared. And we get 1/2 times log, and that's common log, of u plus 2 times log of v. And I guess maybe we should distribute this 1/2 just because some stuff is going to cancel. So we get 1/2 times log of u plus, and then the 1/2 times 2 cancels, so we get log of v. And there we go. We've rewritten the original expression, but without any exponents. We've managed to turn all of the exponents into coefficients. Okay. So there's one last situation that we have to deal with, and that's something like this. So let's approximate log base 2 of 12. Well, I guess before approximating, you might think if we could evaluate this exactly, but what power, to evaluate this exactly, we'd have to figure out what power of 2 would give you 12. Well, again, there's some power of 2 that gives you 12, but it's not a nice number. It's, let's see, I mean, 2 cubed is 8, 2 to the 4th is 16, so it's somewhere between 3 and 4, but other than that, I can't really say. If we want a better approximation than something between 3 and 4, we would need to put this into a calculator and let the calculator do the heavy lifting. But if you have a scientific calculator and you look for the log base 2 button, you won't find it. Most calculators only have a natural log button, that's base e, and a common log button, and that's base 10. So what we would like to do, ideally, is somehow translate this log base 2 into a logarithm that has a base that we have a button for. So either a natural log or a common log. Unfortunately, there is a property of logarithms that lets you change the base. It's rather cleverly called the change of base formula. And it says this: log base a of b is equal to, so first of all, you can choose any new base that you want. So you can choose base e or base 10 or anything, really. And what you get is, choose your new base. I'm going to call it c. So log base c of b. But you have to divide by log base c of the old base a. So sort of what this is saying is you can switch from base a to base c, but the price of doing that is you have to divide by log of the old base. All right, so we said we wanted to switch to a base that we have a button for on the calculator, so let's use natural log, I guess. So that's log base e. The change of base formula says we get natural log of 12 divided by natural log of the old base, which is 2. So I'll punch these into my calculator. So natural log of 12, that's about 2.485. And natural log of 2 is about 0.693. And then if you divide the 2, so natural log of 12 divided by natural log of 2, I get about 3.58496, and, you know, some more decimals after that. Just to show that, yes, we really can use any base we want, let's do this again, but instead of using natural log, let's use log base 10. So log base 2 of 12 should be, according to the change of base formula, common log of 12 divided by common log of 2. If we put those into our calculator individually, let's do common log of 12. That's 1.079 and change. common log of 2 is 0.301 and change. And the quotient, so it looks bad at first because these numbers in this quotient, 1.079 and 0.301, are quite different than the numbers that we got when we used natural log. But when you divide these, so common log of 12 divided by common log of 2, when you take the quotient, what you get is common log of 12 divided by common log of 2. You get 58496 and change. I think I must have transposed these two digits right here. So they do come out to be exactly the same thing. We could use any base at all, but in practice you'll almost always use either natural log or common log because those are the two buttons that you have on your calculator. All right, just to put all of this together, let's look at one other example of how you can use the properties of logarithms. Let's rewrite this expression, common log of x to the third times square root of x plus 1 all over x minus 2 squared. Let's rewrite this with no exponents. The idea here is we can break this into pieces using all of the properties of exponents. And we can slowly make the pieces inside the logarithm smaller and smaller until they're as simple as possible. So let's see. The last operation that this logarithm sees is the quotient. And a quotient inside a log is like a difference outside. So we get log, and it's common log, of x cubed times square root of x plus 1 minus common log of x minus 2 squared. All right. Now we can continue breaking down the things inside the logarithms. In this first one, in this first logarithm, the last operation is this product. And so we can use a property of logarithms that has a product inside. And there is such a property of logarithms. A product inside is a sum outside. So this is log of x cubed plus log of the square root of x plus 1. But, you know, a square root is a power, so let's write it as a power. The square root is a power of 1/2 minus, now in this last logarithm over here, the last operation is this exponent. And the power rule for logarithms says we can shuffle that exponent down in front, so it's a coefficient. So minus 2 times log of x minus 2. Okay, now we're almost done. We can break down the stuff inside the logarithms a little bit more. These first two logarithms both have exponents inside, and we can use those, move those down as coefficients. So 3 times log of x plus 1/2 times log of x plus 1 minus 2 times log of x minus 2. So you can see that all of the properties of logarithms gives us a lot of options for exactly how to write our expressions that involve logs. You can start with something quite complicated inside the logarithm and break it down into pieces so that you have more logs, but each one of them is simpler than the one that you started with. You can also play this game the other way. If you have several different logarithms, you can put them all together into one logarithm so that you have one log instead of several, although the stuff inside the log will be more complicated than it started out. Let's look at one last example like that. So let's rewrite this with a single logarithm, log base 2 of x minus log base 4 of x minus 1. Now you might notice that the bases of these logarithms aren't the same. We would use the difference, the quotient to difference rule for logs because there's a difference here, but these bases aren't the same. And if you look at the quotient to difference rule for logarithms, the bases have to be the same. So before we can do anything else, we need to make these bases the same. either switch log base 2 to 4 or switch log base 4 to 2. It's sort of up to us. And I'm going to switch log base 4 to 2 for no particular reason. So log base 2 of x minus, so I'm going to switch this logarithm to log base 2, so log base 2 of x minus 1. But remember, the change of base formula says in compensation for changing the base, I have to divide by log base 2 of the old base, which is 4. Okay, so log base 2 of x minus log base 2 of x minus 1 over log base 2 of 4, that's 2. Okay, so this is log base 2 of x minus 1/2 times log base 2 of x minus 1. Okay, so now we can use the difference to quotient formula? Well, not quite, because now there's this exponent in front of one of our logarithms. The difference to quotient formula for logarithms doesn't say anything about having a coefficient in front, so we need to put this coefficient somewhere else. We need to get it out of the way. But a coefficient in front, you can use the power rule for logarithms backwards. Instead of a coefficient, write it as a power. So this is log base 2 of x minus log base 2 of x minus 1 to the 1/2. Now finally, we can use the difference to quotient rule for logarithms. This is log base 2 of a quotient. So the positive logarithm turns into the numerator. So that's just an x. And the negative logarithm turns into the denominator. So that's x minus 1 to the 1/2. And that's it. As you can see, having so many properties of logarithms gives us a lot of options.